Oh, is this the moment when you were seeing my slides, but you haven't heard me, right? This is amazing. This is like me doing it completely wrong. Anyway, so you have seen the slides, and I think it's not really important part what I was like telling that. But with that, I would like to welcome Yusuf, right? And he's actually the content and the speaker of this meetup. So I'm really like looking forward to your talk, right? How is it going for you, Yusuf? Like how is your evening going?
Yeah, it's good, going very well. Thank you for having me in this online event about JAX and Trax and other machine learning topics. I'm super
Cool.
excited about it.
Yeah. So with that, I'm just adding your stream, right? And now stage is yours. And yeah, have fun and please share all those amazing learnings that you're having. Welcome.
Yeah, thank you. So let me introduce myself just briefly. Uh, my name is Yusuf. I'm living in Turkey, and I'm a Google developer expert on machine learning. My main focus, my main interest uh, in NLP and speech processing. Um, I'm a user of TensorFlow for a long time, but most recently I also started to use JAX and Trax, and I will talk about these new libraries today. Uh, Hope you'll also enjoy it. I believe that it will accelerate your machine learning research and production development to a great extent, especially if you are working in NLP and speech processing domains. Our My talk will be we'll have actually three subsections. First, I will talk about JAX, which is the uh, giant library with several other machine learning libraries built on top of this library. Then I will talk about Trax, which is one of the many other machine learning libraries that rely on JAX's acceleration and clean code, fast execution uh, paradigm. Uh, and finally, I will briefly talk about some German TTS models I personally trained and published online. In case you might you might find it interesting and want to use them in your projects. So first, JAX might be described as simply the drop-in replacement for Numpy, but many other great features that can boost your productivity when making research or product development in machine learning. Uh, is is accelerated on hardware with XLA, and it supports CPU, GPU, and TPU acceleration out of the box. Uh, all JAX calls are automatically differentiable. It can differentiate. It can calculate derivatives of derivatives of derivatives and more. and it brings all these together to give you a great working environment without worrying about the acceleration and differentiation jobs of the things. Instead, you can focus simply on the innovation you are about to make. One of the best features I love with JAX is tracing functions with make JAX PR function. We can simply define our function and then make another function from that function. And when we call this tracing function, we get a beautifully styled description of what's going on in that function and what it computes. Actually, we will have like a pseudocode, actually, a pseudocode describing the underlying computation run in that particular function. And it really helps understanding complicated calculations in machine learning and what's going on under the hood. And differentiating functions. As you know, with TensorFlow, we need to create a gradient tape if you want to follow, if you want to keep track of gradients of our calculations, and it's almost the same with PyTorch with graphs, but with JAX, we don't need to create any gradient tape or graph. We simply call the import the grad function from JAX and make a function just to calculate the gradient of any given function. Actually, this is function transformation. We simply transform our function to calculate the gradient of that function. Similarly, it supports just-in-time compilation for accelerating the computations on hardware, and all we need to do is just import JIT function from the JAX library and transform our function with calling JIT on it, and then we can use this JIT function to accelerate our computation on hardware. If we set up TPU in the first place, in the beginning of our application, then it will accelerate on TPU. If we connect it to a GPU, then it will be accelerated on GPU. It will be handled automatically by JAX under the hood. And another great feature I love with JAX is simple vectorization of any given function. As you know, we process the data in batches when developing machine learning algorithms to better make use of the hardware performance. Both this is valid both for GPUs and also for TPUs as well. But it sometimes make things a little bit complicated because we have an extra dimension to express the batch size, but we need to operate our calculations on other non-batch dimensions. It may sometimes be tricky, but with JAX you can simply write a function by simply ignoring the batch dimension. Then you can call vmap function on this and get a vectorized version of that particular function. After you vectorize your function, then you can call it with a batched data instead of a single example from your data set. But you'll also enjoy the ease of writing for single samples. Similarly, you can also parallelize your calculations. It's almost the same as vectorizing functions, but this time pmap instead of vmap, we're going to use pmap, and its job actually distribute the calculations across all the known devices you set up for JAX. For example, if you are connected to a TPU with 8 cores, when you transform your function with pmap, this transform function will distribute your batches across all the 8 cores of your TPU. And this is relevant for both vmap and pmap as well. When transforming our functions, we have an extra argument called in axis, and you can specify with this argument which arguments are actually meant to be batched when vectorizing or parallelizing. For example, you may have a batched data, but you can also pass additional arguments, some scalar values. Also, you may pass weights and bases to that particular function, and they don't need to be batched actually. So in access argument is of the type tuple, and it references the transformed it references to the arguments of transformed functions in the specified order. In this case, our first argument will be batched for the first dimension, which is indexed with 0. But the second and third arguments will not be batched as we specify for them the value of none. These goodies actually simply explains why JAX is becoming so popular. Basically, we don't have any gradient tapes. We don't have any bothering with batch dimensions. We can simply JIT our calculations for accelerated hardware execution, and we can parallelize our calculation across all the cores our accelerator. So this is really helpful when you are making research, and speech processing is one of the domains improving and expanding rapidly in the recent times. With the innovations in the domain of NLP, speech processing is also get benefit from these innovations. So to keep pace with these innovations, you need a library that won't distract you from the actual job of finding new algorithms. You should focus on the algorithms instead of simply running them faster. And JAX is a drop-in replacement for Numpy. We have all the quite useful functions from Numpy when dealing with sound signals, like fast Fourier transform. We have Hamming functions and other window functions as well. These are just a few examples, but actually we have all these Fourier transform and window functions, and we can easily implement different feature extraction methods with accelerated JAX API. as JAX is so useful, they are immediately many machine learning libraries built on top of that. I found 6 of them actually, and I believe that there are lots of others that I couldn't notice to date. There are 6 of them, but 3 of them are worth notice in my opinion. Flax is one of the earliest libraries developed on top of JAX. Haiku is the library developed by DeepMind, but actually I couldn't find it that useful. It's more like developed for the particular use case of DeepMind. Elegy might be interesting because they have a clear goal of making the API as close to Keras API as much as possible. And Trax actually is my favorite. It has a clear goal of clean code and high-speed coding, and it's really emphasize NLP research. We will see this in more details. It is developed by the team Google Brain, which is the team behind many innovations, many recent innovations in the field of natural language processing. And is actively used in this team. So it has a real-world use case for one of the biggest research teams in the field of machine learning. You can just find it in github.com Google/Trax. With Trax, we have access to Tensorflow Datasets API under the namespace of Trax.data.tfds, and this means that we have access to many datasets that can be freely downloaded and prepared for our research. For NLP researchers, it has built-in tokenize, detokenize, and autoregressive sample functions. They are really helpful when developing NLP models. Instead of trying to bring many other third-party libraries together and struggling just to make them work together happily, you can simply focus on your research idea. and it has many state-of-the-art model implementations in Trax models. It has configurable transformer architectures, both as a layer, as a block, or full models as well. It has a complete BERT implementation. It has a full working reformer implementation, and many other transformer-based models. You can find them under the namespace of Trax.models, and you can even have a look at Trax.models.research. And under this namespace, you can find many other recent many other implementations of recent NLP models. And it has a stable yet really simple data feeding API. Basically, you need to deal with simply with Python generators instead of custom-made APIs, just to feed some numerical, some metrics and some vectors into your model. You can simply deal with Python generators. You simply write functions for any transformation you want to make to your data, and this function should accept a Python generator as an argument, and you can perform any transformation you want inside this function, and you need to again yield from that generator. And Trax uses the concept of combinators. Basically, there are several combinators called serial, which is basically performs the transformations sequentially, and also there is the parallel combinator, which calculates the transformations in parallel. To demonstrate the easy use of this data feeding API, I tried to write some sample notebooks and publish them on GitHub. And you can find it at this URL, github.com/multi/Trax samples. And German TTS models, my recent work as open source. The problem with NLP and speech processing is that it's constrained by the language. In the computer vision, part of things. You can simply train a computer vision model, and it's expected to work with a similar performance in almost any part of the world. But this is not the case with NLP and speech processing. You need to train new models almost for any new language. And unfortunately, NLP and speech research is heavily dominated by English, and there are only few examples and resources for non-English languages. But this is simply not good, because to make a fair research and to be able to compare our algorithms in a fair environment, we need to test them in other languages, because English is not the best representative of all human languages. There are lots of languages with different orthography, different phonology, different syntactical and semantic rules and use cases. So I started to train NLP and speech models in non-English languages, and German was the first one of these models. I trained Tacotron 2, which is one of the state-of-the-art TTS models. Basically, it converts a given text in German to a feature in the MEL scale, and we call it as a text-to-MEL model. To actually synthesize the real sound waves, we need another model, and it's called multiband MelGAN, which uses the generative adversarial network architecture to learn how to generate sound signals from the MEL input. So we need to use these two models together to generate speech in German with neural text-to-speech. Tacotron 2 is relatively a big model, and it's an autoregressive model, so it might be quite slow for production use cases, especially if you want to make real-time speech generation. Tacotron 2 might be quite slower for your particular use case. So there are other alternatives to solve these problems, and Fast Speech 2 is one of such models, which is actually trained with a aligner model like Tacotron 2. So to be able to train a fast speech 2 model, you need a model like Tacotron 2. So after training Tacotron 2 and multi-band MelGAN, I now started to train fast speech 2, and I will release it soon as well. And also Hi-Fi GAN, which is another model that can replace multi-band MelGAN with a relatively higher quality, actually. I will release it soon as well. Currently, Tacotron 2 and multi-band MelGAN can be found in this GitHub repo, github.com/monatis/German TTS. And I also published them on TF Hub. You can go to tfhub.dev/monatis and find these models. You can it offers both saved model and also TF Lite versions of the models, and it also provides the sample code to demonstrate how to use these pre-trained models. These models are trained on Thorsten dataset, which is donated to the community by Thorsten Müller, and it's really helpful because TTS datasets are really difficult to obtain because they need to be recorded in good studio-like environments for the best quality without other noise and other distracting noisy environments. So after this presentation, if you want to reach out to me, you can always write to me at this email address. I will try to respond as soon as possible. Thank you for having me and attending this online event. Now, if you have questions, I can have them and try to answer them.
Yeah, thank you for your talk. It was an interesting combination of different aspects, right, of building a machine learning models. So there were like a couple of questions. So while people are still like writing new ones, right, I will just like come back and ask the old ones if it's okay with you. So the first question is coming from Harris, and he's asking, most of advantages of JAX seems to be available in PyTorch as well. Are there any use cases where JAX would be better than PyTorch? And I guess you can replace PyTorch with, I don't know, like Keras 2.0, right? Or TensorFlow 2.0.
Yeah. Actually, I tried to talk about this throughout my talk. JAX has a clear goal of clean code and speed. With TensorFlow and PyTorch, there are some limitations that are coming from the backward compatibility issues. JAX instead uses newer approaches of several the algorithmic problems. One of this is stateless random number generator. With TensorFlow and PyTorch as well, we usually use stateful generators, and these are problematic when you switch to TPU, because TPU is not so good at stateful calculations. You need to make all the calculations stateless, and JAX has a stateless random number generation out of the box. So your code just runs on CPU, GPU, and TPU without any particular change in your code. You just write your code once, and it runs on all the hardware you can obtain.
And I guess
also it has like simple function transformations like jitting, v mapping, p mapping for vectorization and parallelization. These are really helpful when you are writing new algorithms for state-of-the-art machine learning research.
Yeah, definitely. And correct me if I'm wrong, all of this research with MLAR, right, and XLAs, right, to make it faster, they're like way more flexible within JAX, right, and in PyTorch and elsewhere, right? Okay, so I guess I have one more question. And this is basically coming more from my side, right? I had a feeling that even with TensorFlow, at least like before like 2.x, there've been like quite a few moments, right, when you'd be like, oh no, like API again changing, right, and we're going from estimators to like Keras, right, from Keras or to elsewhere, right, and JAX feels like even more even newer, right? So it's like even like less, hey, like it's like set in stone, right? So how do you feel? How stable is the API, right? And how frequently do you see that something that worked on early version of JAX, right, it doesn't work anymore, right? Or like how stable basically is the API, and how can you rely on JAX currently?
Yeah, actually, very good question, Davis. TensorFlow has a rapidly changing API, and it's sometimes might be really tricky. Even if your code might be broken between minor version updates. JAX is a newer library, but basically it's rely on several other stable libraries such as Numpy, SciPy, XLA, and Autograph. So it's basically brought together to provide researchers and engineers an end-to-end tool to make a faster development. So it's not invented from scratch, but instead it's composed of several other stable libraries, and this is really helpful as machine learning engineers and researchers. I believe that we are all used to Numpy API, and when you go to JAX, you can simply import JAX.numpy as JMP, which is the traditional way of importing accelerated NumPy in JAX, and you are good to go with this accelerated NumPy implementation. You can simply call any NumPy function with this under the namespace of this JMP, and this is also valid for SciPy, which is a little bit which has some missing functions when compared to NumPy, but it's still quite usable in this at this stage. And plus, you have all other use cases, and actually they are really stable even at this stage, like JIT, PMAP, and VMAP. These are all stable functions for now.
Totally makes sense. Thank you for explaining that. And maybe like very last question, because I'm not sure, most likely you're aware, right? But TensorFlow 2.4, right? They also release experimental.numpy. That should be kind of like having some subset of like NumPy already implemented. I'm not sure how is it like with VMAP and other things, right? So how do you feel? What is like a good use case for TF experimental.numpy versus like JAX, right? Or like how do you at least like mentally kind of make distinction between those two?
Yeah. This is called TensorFlow NumPy actually, and it has the reimplementation of NumPy API. But TensorFlow is a really big ecosystem, in fact, and it's used in many strategic applications in production. So it has really some backward compatibility issues. So yeah, you can change some APIs on the surface level, but you cannot change some systematic implementation details under the hood, and this poses some limitations on the TensorFlow side. For example, with Trax, you can choose to use the use TensorFlow NumPy or JAX as the backend for computation, for the heavy lifting of computation. JAX gives better performance for my comparison work, but Trax also supports exporting models to Keras format for productionize your trained model, and you can even export TF-Lite version from that model converted from Trax to Keras. But to be able to use this feature, you need to first run your model with the TensorFlow NumPy backend at least a batch. So my usual workflow is like this. I first train my model with the JAX backend. I checkpoint my model, then I reload that model from the checkpoint file and run a batch with TensorFlow Numpy and then export to Keras format for further use in production.
It's a very interesting trick, right? Because you're kind of connecting like the best out of the worlds. Yeah. Awesome.
I think this limitation will be removed in the near future soon.
Yeah. Cool. Thank you very much for amazing talk, right? And also giving like all of your answers as well. It was a pleasure having you. So yeah, thank you.
Yeah, thank you so much for having me and this opportunity to talk to this great audience. So have a nice evening.
Have a nice evening. Bye-bye. Cool. So we had like a first talk, and now I'm like really excited to actually invite our second speaker, Shivanji, because she was already like on the backstage like for a while. Hey, how are you doing?
Hi, I'm good.
Nice. It's kind of funny because with all of those internet meetups, it's kind of easy to get people from different locations, but it's still like a good opportunity for us to actually have somebody like local from Munich, right? Because maybe at some point we're going to be back to like real spaces, and we can have like people like asking the questions. Cool. I guess if you would share your screen, right, I can add you to the stream as well. So there's like a button underneath for share.
Yeah, shares.
But today's completely fine. I already had like technical issues in the beginning, so
Entire screen or some entire screen, right?
It depends how you prefer it, right? I mean, you can, if it's a Chrome window, you can share on the application, or you can do like entire screen, and after you make it full screen, so it's gonna work out. Yeah, I think I can see it. So now you can also see it, right?
Yeah.
Okay. So if you try to put it, I don't know, you're gonna show it like it is, right, without full screen. Okay. So
let me try full screen. Play mode. Yeah.
It works perfectly. Yeah, with that, I would say the stage is yours, and yeah, have fun telling all those amazing things that you did within your research group.
Okay. So, hello everyone. I am Shivangi, and I'm a PhD student at TUM, Technical University of Munich. And today's talk is going to be about a recent project that I did with my professor, Professor Mathis, and my industrial advisor, Chris. So this project is about tackling one sort of misinformation that is out there, which is out of context use of images. So let's start. So when we talk about fake images, especially on social media, there are basically two main categories. So first is like image tampering, and an example is shown in this image on the left. And here what you see is what people do is they play around with parts and regions in the image to convey a different message or misrepresent the person. So, for example, in this image, the original image was of a student holding a Black Lives Matter banner, but it was tampered such that it says Lincoln was racist. So, this is one form of misinformation. This is one form of image misuse that is used to spread misinformation, and the second form is where people do not tamper or play around with the images, but what they do is they share this image with a claim which is not at all related to it. So, for example, in this image on the right, you see that there's a person burning a flag, and the original image was from 2016 during some anti-Trump riots, and this was shared in 2018 with a claim that says that people in migrant caravan burnt American flag. So this is also a form of sort of misuse of images that people use to spread misinformation. So, and there's been a case study that analyzed that tweets or links or posts that are shared with images receive more attention compared to normal posts. And also these kind of posts where like there's been image tampering or there's been images that are shared with false and misleading claims, they receive more attention compared to the genuine image posts. So obviously there's a need to detect these sort of misuse of images. And there are already a lot of methods that basically handle image tampering and where they sort of detect which region in the image is manipulated and stuff. So with this project, what we are trying to do is we are basically trying to cater the second misuse of images, where the images are legit, but they're shared with false and misleading claims. So yeah, this project is about out of context image use, where the images are basically genuine and they're shared in false or misleading context. So as an example is this image. So this is an image of Obama from 2014, and this image was shared with a text that said that President Obama is in Maryland to learn something about Ebola vaccine. And after the outbreak of COVID, this same image was reshared on Facebook with the claim that that this person, Obama, is in Wuhan for some bad project. So this is basically the out of context use of images. And with this project, this is what we're trying to detect. So, and out of context image use can also be classified into two categories. So I will explain the categories with an example. So here you see an image of a patient, and the true event that describes this image is given by the text above. So this is actually an image of a patient who is transferred by an ambulance to some infectious disease center in Hong Kong. But this image was reshared with a false claim where it says that Chinese officials are started killing of patients to stop the spread of coronavirus. So one out of context use of images is that the images are shared with completely false claims. And the second is this example. So this is an example of a building, and this building is actually a screenshot from a China-based construction website. And this image was reused to spread one misinformation that this image is basically of a hospital in Wuhan that was constructed in a few hours after the outbreak of this new strain. So the claim is partially true in a sense that the hospital was constructed, but this particular image is not this particular image is not of that hospital, and it wasn't constructed in few hours. So basically these are the two kinds of misuse of images when we talk about out of context, and that's what we're trying to detect with this project. So the standard thing that comes to our mind is, why not collect lots and lots of images and label them and develop some supervised classification method. And to give you an idea, obviously we need huge amounts of labeled data to build a supervised deep learning model. So for example, when we talk about image classification, people benchmark their methods on ImageNet, and this data set consists of around 14 million images. When we talk about object detection, segmentation, then people benchmark their results on MS COCO dataset. And this is also a very large scale dataset, like 300,000 images with 2.5 million labeled objects. So given the nature of the problem that we're trying to solve, there are lots and lots of images shared on social media every day, like Facebook, Instagram, Twitter. But only a handful of them are used to spread misinformation. And right now, these things are being regulated by fact-checking initiatives like Snopes. So Snopes is a fact-checking website. So, and they basically look at each and every post and label them whether it's true or whether it's false. So there are samples available to sort of build a model for this task, but the data set is super tiny. So to give you an estimate, so there are around 300 million photos that are shared on Facebook every day, and only around 13,000 fact checks have been done by this website Snopes in total. So basically, there's a lot of imbalance, and we don't have enough training data to train a supervised model for this problem. So that's where we decided that is there a method that we can use these other set of images that are not shared in misleading context, that are genuine images with genuine posts and claim, and reuse these images to develop a model for our task. So that's the main idea. So we developed a self-supervised training scheme, and the basic idea is we collect a bunch of images, and for every image, we collect multiple captions. And for example, this is an image of a train accident. And so this image was shared with these two captions. First one is talking about that rescue workers at the site of train accident on Great Belt Bridge in Denmark. So this is basically talking about rescue workers. And the second one is the passenger train was stuck by a cargo container in Denmark early Wednesday. So the second caption is talking about passenger train. Similarly, for this image, where basically we have a scooter. So this image was shared with these two captions. Electric scooter programs have become popular in crowded cities like San Francisco. And the other one said that a scooter on the sidewalk in downtown San Francisco. So both of these captions are talking about scooter. So we basically collected such data set where every image is associated with multiple captions. And the reason behind collecting multiple captions per image was to basically build a model that has sort of understanding in terms of varying context, varying vocabulary, varying words. And then what we did is, so basically the top two captions that appeared with the image on the left, which is of train accident, are supposed to be positively correlated, and the bottom two captions, which are about scooter, are supposed to be positively correlated with the scooter image. And the captions with which an image did not appear are supposed to be negatively correlated, right? So basically, this is an image of train accident, and rescue workers are present in this image, and passenger train is present in this image. So we need to build a model that is basically able to identify these sort of objects in the image. Similarly, for the scooter image, looking at the caption, the model should be able to identify that there is a scooter in the image. And I would say that this is like a challenging task compared to like standard image captioning models, because there is a lot of information in the caption, but it is not really useful for basically identifying the objects in the image. So the news captions or in the wild, sort of posts on Twitter, Facebook, and media and stuff are very different from standard image captioning models that are used in machine learning. And the reason why we're learning this association is, I will explain it later. So this association would later be used to detect out of context use of images. So once we train, so first we collected a large scale data set for the task. As I said, like for every image, what we did is we basically collected a lot of images, and then we used Cloud Vision API to do reverse image search for this image. And then we collected multiple captions corresponding to the same image on different websites. So in this example, this is an image of showing buses, and this was fact-checked by Snopes, which basically said that these are the buses purchased by Black Lives Matter to transport members to riots. And this image was shared on this website Daily Hype with a caption that NBA champion arrived at Disney campus, buses were wrapped with Black Lives Matter. And this image was also shared on this website CBC, where it said that Toronto Raptors roll into NBA bubble in the Black Lives Matter buses. So this is how we collected multiple captions per image. And we basically collected images, especially for the topics and keywords where there's a lot of misinformation. For example, when we talk about elections and environment and politics and racism, so these are basically some of the areas where there's been a lot of misinformation, a lot of out of context use of images. So we basically focused on these particular segments, and we collected around 200,000 images for training, and then we benchmarked our results on around 2,000 images. So for training, we did not use any labeled annotations. We only use these annotations for our validation set, only for benchmarking, only for comparing. And for training, basically every image can have variable number of captions. So one image can have 2 captions, 3 captions, 4 captions. But for validation, we ensure that every image has 2 captions. And then there's a reason which I'll explain later. So this is how we do our training. So basically for training, we take the image and 2 captions. We call them matching caption and a non-matching caption. So matching caption is basically the caption that occurred with this image, and non-matching caption is simply a random caption from our data set. We use this pre-trained object detection model, mask-RCNN, to first detect objects in this image. And then we encode the features only for these objects. And we basically generate 300-dimensional embedding for each of these objects. And then what we do is, to encode the textual captions, we use use embedder. So use is universal sentence embedder. This is basically a pre-trained text embedder and is expected to perform really well on out of vocabulary words and news articles text. So we use this, and then we have like a simple text encoder, which is a fully connected layer, and we generate 300-dimensional embedding for each of these texts. And then now that we have same dimension for objects and for text, what we do is we basically combine them. And the way we combine them is with a dot product. And this dot product basically gives us caption object scores. And once we have these caption object scores, we then apply a max operator to obtain image caption scores. So basically identify which object is most important for the image corresponding to a given caption. So that's what these scores tell us. And then we train it with the simple max margin loss, where we ensure that the score for the matching caption should be higher compared to the score for the random caption. And let's see how the results look like. So once we've trained this model, we expect the model to assign high scores to the objects of interest and low scores that are to the objects that are not at all related to it. So I have the same example from the previous slides, which is like of this train accident and the scooter image. So let's look at this train example first. So these were the top 3 objects detected by the model, and a positive score is given by the model for the train, which is the accident, and negative score is given to this helicopter and to this person. And obviously, if you look at the top caption, it is talking about the rescue workers at a site of train accident, but it has given a negative score to this person, so which is like technically it is wrong, but it's sort of like a very difficult keyword for the model to comprehend, because it is talking about rescue workers. And had it been maybe a simple word like person or something, maybe the model would have been able to identify it. And the second image is of scooter. So here we have the scooter, the legs of the person, the handbag, and this pole. And both of these captions, as we've seen before, are talking about scooter. So in this case, the model was able to give a positive score to the scooter and negative score to the other objects. And here we have some more examples. So in the previous slide, I showed the image with 2 captions, and both of those captions were basically correct. And now in this slide, the captions that you see in the green are true captions, and the captions that you see in the red are basically the false captions. So the first image is of like 2 girls crying, and the original caption was that the residents cry outside a reunification center after deadly shooting. And the second caption is also talking about these people. So where it says that the immigration authorities were checking citizenship papers of people affected by mass shooting in El Paso. So first one is being addressed to residents, which is also these people, and the second one is addressed to people, which is these 2 girls standing. And these are like few of the top objects detected by the model. Like there are cars in the background, and then there's this person detected. And the model was able to give a positive score to the persons and a negative score to the cars in the background. Similarly, for this image, a patient transferred to this infectious disease center in Hong Kong, also talking about patient. And then Chinese officials are started killing patients to stop spread of virus. It's also not talking about patients. So these are the top objects detected, and the model is able to give a positive score to this person lying on bed, and that the person who's taking him to the wherever, and negative score to the other objects such as this chair and this handbag and others. So so with the training strategy that I explained in the previous slides, we were able to build like a decent model that is able to correctly identify the relevant objects in the image. And then once we identify the important objects, then at test time, what we do is we basically, so most of the out of context use of images always talks about the same object in the image. So, for example, in this image, so this is an image of buses, and the fake or the untrue text was that the buses purchased by Black Lives Matter to transport members to riots. And this is talking about buses, although this is a false claim. And the second text says that the Toronto Raptors roll into NBA bubble in Black Lives Matter buses. And this one is also talking about buses, but this is saying something different, and this is a true claim. So what we do is we basically take this image and both of these captions to and feed them to our model, and we detect out of context image use. And how we do it, we follow the same guideline. We take the image, we detect the objects in the image, and then we take both of these matching captions. So basically, as I said, that the first matching caption is false and the second matching caption is true. And then what we do is we basically feed them to our trained model, and we then identify top objects for both the captions. And these are basically the most relevant objects for caption 1. So the most relevant objects for caption 1 are shown in this red box, and the most relevant objects for caption 2 are shown in this green box. And then what we do is we take an additional pre-trained model to compute sentence similarity or sentence semantics. And then what we see is if both of these texts are semantically different and they convey different messages, but what they do is they basically identify same objects in the image, then we say, oh, this is out of context use of images. And otherwise, we say that this is not out of context. So this is the main idea for the method. And we basically evaluated this method for different text embeddings. So we used GLA, fast text, and use embeddings. And the first column, the second column here, you see the match accuracy. So this is basically the loss that the model was trained with, that the score for the matching caption should be higher than the non-matching. And then there was this context accuracy. So basically we only evaluate on this. We do not train our method for this context loss. And we achieve about 82% accuracy. And here k equals to 1, 2, 3 basically identifies that are we talking about top 1 object, top 2 objects, or top 3 objects. So the more objects you consider, the more sort of liberty you give the model to make a mistake, and your performance also sort of increases, because there is more possibility to sort of have the same object in the grounding. And then we also did one more experiment where we basically evaluated the effect of dataset size. And we know that for supervised methods, the bigger models and bigger datasets help. But we wanted to check for this particular use case as well. And we noticed that having a bigger dataset also helps us improve our model. So using 100% of our data, we got around 73% accuracy, whereas using only 10% of our data, we got around 67%. And then we also compared our method with other rumor and fake news detection methods. And our method is relatively better, and the main reason that this approach stands out from the other method is basically we're using objects, and rest of them are operating on full images. So the detecting objects basically helps the model to focus only on the important parts in the image. So this is the story so far. I mean, we're around 82% accuracy, but obviously this is not deployable. No one can use this to in real time to detect these misuses. So obviously, one thing that I realized from this project that visual grounding is a challenging task especially for news captions. So an example, this is an image of a metro, and the caption that this image was shared with was that LA Metro Ride offers a small portrait of this sprawling city. And this is not directly describing the objects in the image. For example, the model needs to understand that the metro is a synonym for the word train, and identify and ground this object. So this is like a very easy task for humans, but for models, this is like a very challenging task. So the model was able to detect like the correct object in this case, but yeah, it is difficult for models to basically find out relevant objects from these captions. And the second thing is we obviously need a self-supervised method because the supervised data set is very tiny, especially for this problem that is basically publicly available. So yeah, we have very limited number of images that are fact-checked, and right now I'm using them in my validation set just to evaluate the performance of the model, and I'm not training on these few images. And one thing that we used during our model is basically mask RCNN to detect objects in the image. Although it was able to detect these cars in the background, but the second person, who is very clear to us, the model missed detecting this person, and so using these pre-trained models sometimes miss to detect these objects, and therefore obviously we need to sort of use like an ensembling technique with a variety of models, or come up with something else so that the relevant objects are not missed. Second thing is that during training, during test time, we were using this sentence similarity model, which is sentence BERT, and which is shown in this pink color on the right. And this is also a model that computes the similarity between the two texts. Although it is useful, but this is also a model. We cannot get performance beyond whatever this model gives us, because we are using the prediction made by this model as sort of like gold standard. So yeah, so we need to remove this and come up with something automatic that does this task in the future. And right now we're taking an image and two captions and letting the model predict whether this is an out of context use or not. But what we can do in the future is like identify which of the two captions is basically false. So that would be actually interesting, and that would help the people to use this in real time. So to summarize, in this project, we basically proposed a new task of detecting out of context use of images. We created a large scale data set for benchmarking. And we proposed a new self-supervised learning scheme to detect out of context use of images. That's mostly from my side. And I would like to thank my advisors and others who basically helped me through in and throughout this project. So that's it from my side. If you have any questions.
Yeah, thank you for amazing presentation and also for providing or building up this like a data set, right? And forming like a new task, right? Now I guess like it's like with machine learning, as you already said in the beginning, if there is like no data, right? If there is like no ImageNet competition, it's like hard to make any progress, right? Because it's just like bouncing your ideas, right? So hopefully like now it's easier. So there were like some questions, but while people see writings, and since we like with YouTube stream is a bit like in the future, I will ask a couple like from my side. I'm not sure if you're aware. So like OpenAI has this like a clip model, right? When they were like training transformers like on text, but also like on images, right? So it's gonna get basically different part of the image like through transformer, right? And it's gonna be having like self-attention as well. So I was wondering if you did try to use something like as OpenAI's clip, right? Because it also would allow you.
So this was like a very basic project. So most of my time for this project was specially focused on formulating the problem, like what kind of thing do you want to address, which is like this out of context use and stuff like this, because there's nothing out there right now that detects these uses. And the second main effort that we spent was basically on collecting this data set. So like what kind of images you need or where do you collect data from. So algorithmic improvement, yes, this is up for future work and that's what we're working right now. But yeah, I haven't tried this clip idea or self-attention or anything fancy. So this is right now, it's a very simple, basic model.
Okay, makes sense.
Yeah.
Because like first you need to collect a data set and only after it's gonna become a bigger thing.
Yeah, exactly.
Yeah, makes sense. So there's like another question from I guess I can pronounce it as Roscoe, right? And he's asking basic. I mean, that was like a question about before, a comment from his side more. Hey, is it like a context, right? Or you just like do a binary classification of positive, like a negative, like a sentiment, right, in the caption? And he's also suggesting basically to take a look reliability of the speaker, right? Or maybe I don't know if you're gonna go like extra mile and say, if you have like a multiple messages, right, you can also try to compare which one is like a bit of like out of the scope on the message level, right? Because sometimes just like a pair of text and image, right, it's like hard to say which one is wrong, which one is correct, right? Because it's not always the same problem, right?
So to actually identify the truth value of a claim, the first thing so this is something which we might do in future is the reliability of source. Where is this caption or information coming from? Is this a reliable source or not? And the second thing would be like to take into consideration timeline. How old is the image and how recent is the text? So if obviously the image is like 10-20 years before, is taken 10-20 years before, and the caption or the post is like, I don't know, like last month, then obviously there's a strong signal that it's out of context or it's some false claim. So yeah, these are the things out there, and we are not identifying whether we are not doing sentiment analysis in any case. We are not saying whether that this is a positive or this is a negative sentence. No, that is not what we are doing. What we are doing is we take an image and we basically have two captions, and we identify whether these two captions, one of these two captions is out of context with respect to image. So that is the main task that we're trying to. So the formulation is a bit different from standard machine learning tasks that basically you see out there. You take an image and you take two texts and you identify whether it's out of these two captions are out of context with respect to this image.
Yeah, exactly. I was about to say, right, that it's not really sentiment analysis just for the text, right, but with respect to the image, right? Hey, is it like, does it correlate, right, or is it like negatively correlates, basically?
Exactly.
Cool. Sounds good. So how do you feel what's going to be like the biggest challenge for the next part, right? Because you mentioned it's like a future work, right, and more complicated like algorithm, right? Because like now we have a data set. So what do you foresee like the biggest challenge or the biggest bottleneck for the next steps?
So sometimes actually, we haven't made this data set public, but sometimes you see, because obviously we have a lot of captions talking about politics and stuff like this. So this depends a lot on the timeline from where you collected this data set. So when I started collecting this data set, I collected basically images from past 2 or 3 years. So for this subject politics, I had a lot of text that talked only about Trump. President Trump did this, President Trump did that. And then I realized, oh, this is problematic because this is going to overfit only for this person. So one of the major challenge was to collect a data set that is diverse enough, that spans through a variety of topics and that spans through a variety of identities and people. So obviously, so first thing was this, and so we basically said, let's not collect images for 4 years, let's collect images for 10 years, so that we have like a wide variety of people in our data set. And that's something that we faced during this project.
Yeah, pretty cool. Maybe just a follow-up to this direction. I remember, because you mentioned like Trump and politics, right? So it was like quite a discussions like on Twitter, right? And Twitter even like did ban Trump like at some point, right?
Yeah.
And what I do remember is that they have this connection to this I'm not sure, like group, right? Or like a service that checking how valid the claim is, right? Do you know if this organization or whatever, how is this like structured, if they also providing this data for researchers, right? Because it might be also like an interesting way to, enrich your data with something like bigger than that, right? So like Twitter and Facebook, I think they have it like kind of like as a big part of their current problems, right, in terms of misinformation. So is data available for researchers, or it's kind of hard
this
to say,
data
right?
will be out soon. We're just like in the final steps of releasing this data set. Like I think in coming weeks we might make an announcement about the data set release. Yeah.
Nice. Pretty cool.
Yeah.
Awesome. Thank you again for your time, right? And also for sharing, your passion about this like data set and about this problem. It was amazing, at least like for me. So definitely thank you for your time.
Thanks for having me.
Have a good evening.
Good evening.
Oh, sorry. Like I just cut you off. Goodbye. Bye-bye.
Bye. Bye.
Cool. Thank you again for joining us. It was amazing to have you spend with us like one more evening. As I said in the beginning, or just like showed you a slides, that we always looking for speakers, right, and for also people to support us, right. So if you have feedback, especially about technical difficulties in the beginning, just like let us know. And with that, I wish you a nice evening and stay safe and rock on 2021. Have a good one. Bye.